Okay, let's look at Chapter 11, Physical and Chemical Agents for Microbial Control. So what should we consider when we're trying to control microbes? Well, we can talk about physically controlling them, or we could talk about chemically controlling them. We could talk about mechanically controlling them. We could talk about how do we destroy them, how do we contain them, right? How do we just decontaminate from having microbes? And so when we think about who microorganisms are that we're wanting to control, we typically concentrate on those that are capable of infection and spoilage. And these include vegetative bacterial cells, okay, and endospores, fungal hypha and yeast, your trophozoites and your cyst of the protozoans, worms or helminths, viruses, and prions. So when we're thinking about this chapter, we're going to talk about physical agents of control. We're going to talk about mechanical agents of control or removal techniques. And we're going to talk about chemical agents of control. So, who of the microbes is the hardest to kill and who is the easiest to kill? Or maybe I should say, who is the most virulent, who has the highest resistance, thus will be the hardest to get rid of. And by far, those are going to be your prions, which remember are not viruses but viral particles, non-viral particles, and then your bacterial endospores. And remember, those are the genuses of bacteria that tend to go dormant when the conditions get bad. And again, we'll go into more detail. Your moderates are like your protozoans, your bacteria that don't have endospores, your mycobacterium and other gram-negatives, some of your staphylococcuses. And then by far the easiest to kill, the least resistant, easiest to kill would be your bacterial vegetative cells. And remember, that's most bacteria just when they're eating and growing and reproducing and they don't have endospores. That's who's usually the easiest to get rid of. Okay, so Ms. Bradley, how hardy, how virulent are bacteria that have endospores? Well, again, I would never want you to know this chart, but I do want you to look at how long it takes to kill something that has endospores opposed to when it's just a non-endospore former. So, for example, if we're trying to control something with endospores like Clostridium, yeah, I'm sure you've heard of C. diff, okay, Clostridium, then we would have to make sure that we had the temperature at 120 degrees Celsius opposed to 80. Radiation would be 4 times as much to try to get rid of endospores. Gassing, if we were trying to gas it, almost twice as much gas. And if we were using the sporicidal liquid, we'd have to use it for 18 times the amount of time that it would take to get rid of a vegetative form. So again, this is just a way of looking at it. I'm not going to make you know it, but just to try to show you how one is so much hardier or more virulent than the other is. So when we hear the word cidal, cidal means to kill. And when we think about the word cidal, then we think of things that are to destroy, to completely do away with. So for example, if you hear something that says bactericide, fungicide, viricide, what we're saying is that our goal is to kill that organism. All right, the next definitions are all very, very similar, but when you look at them, you want to look at key words to help you in the definition. So, for example, process to destroy all viable microbes. That's sterilization. Disinfection is when you're trying to kill most. But remember that disinfection is a physical process. Okay, a physical process. And again, when I'm studying these, I tend to try to think in terms of what keywords am I trying to kill all? Am I trying to kill most? Am I doing it physically? Or am I, is it something that can handle this particular chemical or not? The word antisepsis is, again, the direct removal on body surfaces, wounds, surgical incisions. You're trying to kill most of them, but you know you're not going to be able to kill all of them. When you hear the word static, static means to slow down. So what you're thinking about there is you're not trying to kill them all. You know that you're not going to be able to kill them all. But instead you say, hey, look, I want to keep them from multiplying. I want to keep them at bay. I want to keep them from increasing their number. If anything, I want them to stay the same or get less. So these are going to be words like sanitation and degermination. Sanitation is the cleaning technique that removes microorganisms from inanimate surfaces. Inanimate. That means non-living surfaces. So for example, I can sanitize the toilet. I can sanitize the sink. Again, am I removing all of the bacteria or microbes? Probably not. But again, sanitation is on an inanimate object. I would never sanitize you as a patient. Degermination, on the other hand, is when you're trying to reduce the load off of living tissue. So you're trying to degerm. You're trying to remove it mechanically by removing it from living tissue. So again, when you're looking at these vocabulary words, make yourself an association. Am I trying to kill all? Am I trying to kill most? Is this a living, animate surface, or am I trying to do it on an inanimate surface? So again, try your best to make sure you can distinguish between these vocabulary because they are very, very similar. So again, this is an example. There's the definitions, and it gives the definition. There are the terms, it gives the definition, and then it gives an example of decontamination, an example of sepsis, an example of asepsis or antiseptic. Okay, and I think that's a great table to make sure you know why you're doing it. So for example, before you give me a shot, or take my blood, you're going to degerm me with alcohol wipes. Okay? Are you removing all microbes from my skin, or are you removing most? That's right, you're removing most, and again, I'm a living surface, therefore that's called degermination. So again, I like this table. I like it a lot. Microbial death. Okay? Microbial death is hard to detect because microbes don't really give you a warning sign that they're dying. But remember that microbial death would be their permanent loss of reproductive capabilities. Even when conditions are optimal for growth, like they've got plenty of moisture, plenty of heat, plenty of food, when you see that they're not reproducing, that's considered microbial death. So there's several factors that we would keep in mind when we're thinking of microbial death. Number one, how many microbes are we trying to kill anyway? Is it a lot? Is it a little? We call that the load. Okay? The nature of the microorganisms. Are these common microbes, or are these real virulent microbes? Are they, what's their nature? Can they handle the temperature and the salt, or can they, in other words, like, are they hardy? Right? Are they virulent, or are they easy to kill? What is the temperature and the pH of the environment? Is this going to encourage growth or discourage growth? Concentration. How concentrated of a solution am I going to have to use? How is it going to kill? That's mode of action. How is it going to get rid of the microorganisms? And am I going to be using a solvent or an organic matter or an inhibitor? What exactly is it that I'm going to be using to try to cause this microbial death? So again, looking at this chart, it's kind of nice to look at, sterilization. You're hoping to get to zero, right? Number of organisms. You're hoping for it to just decrease at a pretty steady rate. If we're thinking of loads, like numbers, well, are we trying to kill a high load, or are we trying to kill a low load, right? For example, the load inside the, floor of the ER is probably going to be greater than, the load inside of the operating room. So the ER waiting room versus the actual operating room. Are you trying to kill something that has endospores, or are you just trying to kill an average, ordinary vegetative cell? Okay, So when we think of action, modes of action, okay, there's several that we have to consider. Okay, number one, cell walls. Can we attack the cell walls? Because if we can attack the cell walls and then we can flood the cell is going to burst or lyse. Okay, so that's number one. Why would we want cell wall action? Well, because we don't have cell walls. We're animal cells. Therefore, our cells would not have cell walls. Theirs would. So if we're using something to attack cell walls, then it won't attack us, hopefully. Okay, number two, cell membranes. Typically what we're looking for here is we're looking for surfactants that are going to break down that phospholipid bilayer, break down that cell membrane. Okay, number three, if we can't attack the wall and we can't attack the membrane, then let's attack their ability to make proteins or to make nucleic acids like DNA or RNA. So what would that do? Well, that's going to keep them from replicating. It's going to keep them from transcription. It's going to keep them from translation. It's going to keep them from making proteins, protein synthesis. Well, what if we can't do those three methods? Well, let's mess up their proteins. Once they've made their proteins, let's denature them. Let's warp them out of shape. Okay, well, if we can't warp them out of shape, is there anything else that we could do? And we'll talk about that later, but for sure those are the four major modes of action. So, let's read this question. If you wipe your hands with an antimicrobial cleaner, what are you doing? You wipe your hands, okay, hands, are those living or non, right, animate or inanimate, with an antimicrobial cleaner. You are, that's right, antisepsis. Right? Antisepsis. So again, you're trying to kill most, and you're doing it on a living surface, an animate surface. Okay? So, when we're looking at physical methods of control, remember you got physical methods, chemical methods, and mechanical methods. So when we're thinking about physical methods, we're thinking of things like heat, moist and dry versus cold, versus desiccation, which is drying out, radiation, and filtration. So let's look and see which one works best. Okay, moist heat versus dry heat. Okay, moist heat, you can have lower temperatures and you can expose it for a shorter amount of time, and what's going to happen is you are going to coagulate, which would mean to cause it to stick together or to denature their proteins. When you're using dry heat, you're going to have to use high temperature, and you're actually going to have to incinerate them. You're actually going to have to alter their protein structure that way. Okay, so dry heat versus moist heat. By far, moist heat is most effective. Moist heat is most effective. Look at the difference. If Miss Bradley puts those microbes in the autoclave, I can do it at 121 degrees Celsius, and I only have to do it for 15 minutes before I kill them. If I'm putting them in an oven, right, dry heat, I've got to do it for 600 minutes. How long is that? 10 hours, right? See the difference? If I'm going to kill them, if I do moist heat, I can just do it for 15 minutes. Okay, think of like pressure cooker. But if I do dry heat, I've got to do it for much, much longer periods of time. All right, thermal death time versus thermal death point. Thermal death time is the shortest length of time required to kill all of the microbes at a specific temperature. Thermal death point is the lowest temperature required to kill a sample in 10 minutes. So again, it has to do with how long to kill all versus how long to kill all of a particular sample size. So, what is the magic number that I expect you to remember? I absolutely expect you to remember that an autoclave, we're going to do it at 15 pounds per square inch of pressure, 121 degrees Celsius for 15 minutes, or at least 15 minutes. Remember that steam must reach the surface of whatever it is that's trying to be autoclaved. We know that whatever we do this to cannot well, let me back up. It has to be able to handle the moisture and the heat. And again, what is it that we're doing when we autoclave our microbes? We are literally denaturing their proteins. We are warping their proteins out of shape. We're messing up their membranes. We are messing up their DNA. Okay? What if we don't use pressure? Okay, what if we don't use pressure? Well, again, there's this process called tyndallization, but the key here that I want you to notice is that you've got to do it for 30 to 60 minutes, incubate it for 24, and you've got to repeat this for 3 days. So if we don't use pressurized steam, this is a much, much longer process. Well, Miss Bradley, what about boiling water? In the movies, they always talk about boiling water. But remember, you're going to have to disinfect. You're going to have to do boiling for 30 minutes. 30 minutes before you kill non-spore forming pathogens. So you're going to have to boil those peas, boil that, whatever it is that you're using, for 30 minutes at least. And even then, you may not have killed all the bacteria on them. So again, by far, pressurized steam, right, is the most effective. Okay? What about pasteurization, Miss Bradley? Pasteurization. I hear, like my milk is pasteurized, my orange juice is pasteurized. Well, the key here is you've got to be very careful because you do not want to get it to 100 degrees Celsius because if you do, you actually alter the way the food tastes. Right? So we can't do milk and orange juice and things like that at temperatures above 100 degrees because if you do, you're actually going to destroy how that food tastes. So what we often do is what we call a flash method, or if we do an ultra pasteurized method, notice it's only for 2 to 5 seconds. So again, this is not something typically we do at home. This is a much more controlled environment. But pasteurization, that's why it's so important because you don't want to alter the flavor of the food, right, or the beverage. You want it to still taste like milk, taste like orange juice, taste like, buttermilk, whatever. And you have to be careful that you don't alter the flavor. So again, this is just kind of a nice little chart to help you with moist heat versus dry heat. Okay? Dry heat, again, things like incinerators, like that thing that we use on our desk when we're trying to sterilize our loops. So remember that an incinerator often involves a flame or an electrical heating coil. It is a very common practice that we do in micro labs. We certainly do it in ours. It mentions the fact of possibly doing a hot air dry oven. We don't really do that. You do that at home when you're cooking, but we don't do dry ovens here. Again, you're causing the proteins not to denature as much as coagulate or clump together. So there's an example of an incinerator. All right, and again, it just kind of gives you times. So in other words, it kind of shows you that if you use a dry oven, you're going to have to do it for 2 to 4 hours. Whereas, for example, with our incinerators, they can get up to 800. Some small incinerators can get up to 800 degrees Celsius, like furnaces can get up to 6,500 degrees Celsius. So again, it kind of depends on what you're doing. Now, what would be the downside, for example, to using a dry oven? Well, it's poor. You don't want to use an oven if it's something like rubber, plastic, liquids, if it's something that, is time sensitive and you don't have 2 to 4 hours to waste. Again, and so remember that for every benefit, there's also a disadvantage for each one of these physical forms of control. Okay, cold. How many of y'all remember me telling you that microbes do not die in the cold? They simply slow down in the cold. And that's important to remember, that just because you put something in the refrigerator or freezer does not mean that you're going to stop the microbial action. Desiccation is the removal of water from cells. And remember that for many cells, you have to be careful because that water, when it freezes, expands, and you don't want to actually burst the cell. And then again, lyophilization is called freeze drying, or a form of preservation that needs to be considered if you has something that has water in it. All right, so let's see about this one, and then we'll stop on this part and go to our next video. Which of the following accomplishes microcidal effects? And there's the word, cidal, so we're trying to kill. Which of these accomplishes microcidal effects? Boiling, pasteurization, incinerator, freezing, or desiccation? Okay, good. You said boiling, pasteurization, and incineration. All three of those are responsible for killing microorganisms, whereas your freezing and desiccation just slows them down. All right, again, I'm going to stop here and pick up with the next section in the next video.